Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 44. In this lecture, we'll discuss thermodynamic work and the first law of thermodynamics. These topics are covered in Chapter 20, our textbook by Surway and Jouet. Recall from our last lecture that a thermodynamic process is any manipulation of the pressure, volume, and temperature of an ideal gas. In principle, one could change the number of molecules in the ideal gas, but in this class, we will almost always assume that the number of moles or the number of molecules in the ideal gas is kept fixed. Also recall that we like to describe thermodynamic processes using PV diagrams. By following the graph on a PV diagram, you can see clearly how the ideal gas is being manipulated. And of course, remember that pressure, volume, and temperature are related by the ideal gas law. So at any point along this graph, if you know what the volume and the pressure are, then in principle, you can calculate the temperature of the gas. So PV diagrams give us a very precise, concise description of how the ideal gas is being manipulated. Now, in our last lecture, we didn't say much about how the gas is actually manipulated. One way is through heat. In other words, we can change the thermal energy of the system through thermal conduction by adding or subtracting heat from the system. Another way the gas could be manipulated is by performing work on it. Performing work is the main topic of this lecture. Before talking about thermodynamic work, we need to recall the fundamental definition of work from our mechanics course. Imagine that there's a box sitting on the floor and that a force F is applied to move the box. The work that is performed by the force is basically a measure of the influence of the force on the box. So if we want to know how influential or effective the force is in terms of moving the box, we need to calculate the work performed by this force. It turns out a nice way to measure the influence of the force is to simply take the force and multiply it by the displacement of the box. So on a very conceptual level, you can think of work simply as force times distance or force times displacement. A little more precisely, though, work needs to be defined as the integral of F dot ds. F, of course, is the force, and ds is an infinitesimal displacement. This formula accounts for the fact that the force might be a variable force, so its magnitude and its direction might change, and it also accounts for the fact that the displacement might not be just in the x direction. We do need to calculate the dot product between these two vectors, so we should first write out the vectors in terms of their components and then calculate the dot product. We can calculate the dot product by multiplying the x components, then multiplying the y components, and then adding those together. For now, for the sake of simplicity, we'll assume that the y component of the force is 0. So we'll assume that the force points only in the x direction, in which case the work performed by this force on this box is equal to the integral of fx dx. Now we want to apply this definition to an ideal gas. To do that, imagine once again that we have a cylinder filled with some ideal gas, and the gas is capped by a piston. So the piston is basically a disc that seals the gas inside, but is free to move left or right. We've discussed this kind of a setup before. Here I'm placing the cylinder on its side and then applying some force F to the piston. So I'm imagining that the gas is being compressed by this force here. The work that is performed by this force on the gas is once again given as the integral of fx dx just as before. However, I now want to express this definition in terms of thermodynamic parameters like pressure and volume. Recall that pressure is defined as force divided by area. By rearranging this expression, I can express F sub x simply as pressure times the area of the piston. As this force is being applied to the piston is moving by some distance dx, and as I do that, the volume of the gas is changing. The change in the volume of the gas can be seen here as essentially this region over here. So the volume between the initial position of the piston and the final position of the piston is essentially dV. It's the change in the volume of the ideal gas. Now note that as the piston moves in the positive x direction, the volume is decreased. So we would say that if we take A and multiply by dx, we would get a negative change in volume, which will represent as minus dV. So by writing A dx simply as minus dV, we finally arrive at our most important definition for thermodynamic work. Henceforth, whenever we manipulate the pressure, volume, and temperature of an ideal gas, we can calculate the work that's performed by taking the negative integral of P dV. Henceforth, when we talk about the work performed by an ideal gas, what we mean is the negative of the integral of P dV. So we're imagining that an ideal gas is somehow being manipulated in a thermodynamic process. Its volume is changing from some initial volume to some final volume, and the integral of pressure with respect to volume is essentially the work that's performed. Now, there is some vocabulary here that you must be familiar with. People will often talk about the work that's performed on the gas and the work that's performed by the gas. When they're talking about the work that's performed on the gas, they are usually talking about a positive value for work. A little more specifically, what they're talking about is a gas that is contracting. As a gas contracts, its volume decreases, so we can say that delta V is a negative number. If dV is negative and there's a minus sign on the outside of the integral, then work will be a positive number, and that's described as work that's performed on the gas. On the other hand, when people talk about work performed by the gas, they're talking about an expansion of the gas. As the volume becomes bigger, dV is a positive number. Since there's a minus sign outside the integral, work itself becomes a negative. For the most part, if you're faithfully using this equation to calculate work, you don't really need to worry about the distinction between work performed on the gas or work performed by the gas. You can simply talk about positive work or negative work. However, in case you come across this terminology in your reading, you should know what they mean. Another important fact is that work is essentially the area under the PV graph. Recall from your calculus class that the integral of some function is essentially equal to the area under a graph of that function. Similarly, when we talk about the integral of P dV, we're basically talking about the area under a graph of P versus V. This is in fact one of the reasons why we like PV diagrams, because by looking at a PV diagram, we can quickly tell what the work was. For example, in this case on the left, we can quickly see that in this process, this area here is equal to the work that was done in the process. Now, for more complicated situations like this one here, you may actually have to carry out the integral, but in general, remember that the area under the graph is basically the work that was performed in that thermodynamic process. In our last lecture, we were introduced to 4 fundamental thermodynamic processes. I mentioned that these processes are important because they're essentially the building blocks for much more complicated processes. So now let's do a series of 4 practice problems in which we calculate the work that is performed in each of those 4 fundamental processes. To begin with, suppose n moles of an ideal gas is initially at volume V sub I and pressure P sub I. So I'm not giving you numerical values. I'd like to solve this problem in terms of variables. The pressure of the gas changes to P final in an isochoric process. So here I'm telling you that we're manipulating the gas in a way that its volume does not change. Calculate the work performed in this process. We know that in thermodynamics, work is equal to minus the integral of P dV. We are talking about an ideal gas, so we can express P as a function of V. After all, if we want to carry out this integral, we have to know how P depends on V. According to the ideal gas law, PV is equal to nRT. So I can rearrange that expression and write pressure as nRT over V. Now this is an isochoric process, so notice that I've placed a subscript I over here because the volume is going to remain at its initial value throughout the process. And also note that the initial and final volumes are both equal to V sub I. Now this turns out to be a very easy integral to do. Hopefully you remember from your calculus class that whenever the two limits of integration are equal to each other, the integral is simply equal to 0. So what we're finding here is that in an isochoric process, work is not performed. If you want to perform work on an ideal gas, you must allow the volume to somehow change. Remember that a change in volume is essentially equivalent to a displacement of the piston. Without that displacement, it's simply not possible to perform work. Next, let's calculate the work that's done in an isobaric process. Suppose n moles of an ideal gas is initially at volume V sub I and pressure P sub I. The volume of the gas changes to V sub F in an isobaric process. Calculate the work that's performed in this process. Note that we're talking about an isobaric process, so the pressure does not change. So we can say that P final is equal to P initial. Once again, we'll start with the basic definition of thermodynamic work as the negative of the integral of P dV. Here I'm going to replace P with P sub I. This reminds me that the pressure is not changing in this process, or that throughout the process, the pressure is simply equal to its initial value. Of course, P sub I is some constant, so I can bring it out of the integral. And then I'm left with the integral of dV, which is simply V. When you plug in the limits of integration, what we get is that the work is equal to minus P initial times the change in the volume of the gas. Note that if the volume expands, then V final is greater than V initial, which means this quantity here will be a positive number. If that quantity is positive, then the work is going to be a negative number. So whenever the volume expands, work is negative, and conversely, if the volume contracts, work will be positive. So now let's look at an isothermal process. Suppose n moles of an ideal gas is initially at volume V sub I and pressure P sub I. The volume of the gas changes to V sub F in an isothermal process. Calculate the work performed in this process. So here we have a process in which the volume is allowed to change and the pressure can also change, but the temperature of the gas is not allowed to change. The calculation this time is a little more challenging, but once again, I'm going to start with the thermodynamic definition of work as the negative of the integral of P dV. Now note that the variable of integration here is volume, so the integrand, the thing that's being integrated, must be expressed in terms of volume. The limits of integration should also be expressed in terms of volume. In short, everything in an integral should be expressed in terms of the variable of integration in order for you to successfully evaluate the integral. Now, according to the ideal gas law, PV equals nRT. By rearranging that equation, I can express pressure as nRT over V. Now notice that I've placed a subscript I on the temperature to remind myself that the temperature is constant here. We are talking about an isothermal process, so throughout the process, the temperature will always be equal to its initial temperature. So placing the subscript I on the T helps me remember that the T must be a constant. Now the gas constant, of course, is a constant, and we will assume that the amount of gas or the number of moles will not change, so N is a constant as well, which means I can now write this integral as minus nRT sub I, the integral of dv over v. So I've taken all of the constants out of the integral, and now hopefully you remember from your calculus class that the integral of dv over v is equal to the natural log of v. So now we have minus n RT initial natural log of v. Of course, I need to plug in the limits of integration, which are simply v initial and v final. When you plug in the limits of integration, you get minus nRT sub I times the natural log of v final minus the natural log of v initial. Now, hopefully you remember some of the properties of the natural log. The natural log of v final minus the natural log of v initial can be expressed as the natural log of a ratio. So this expression can be written as minus nRT initial times the natural log of Vf divided by Vi. According to the ideal gas law, PV equals nRT, so this nRT here can be expressed simply as PV. If we're talking about the initial temperature, then we should be talking about the initial pressure and the initial volume. So finally, we find that the work performed in an isothermal process is equal to P initial times V initial times the natural log of V final divided by V initial. Once again, note that if the volume expands, then the work is negative. If the volume expands, then V final must be greater than V initial. So this ratio will be a number greater than 1. The natural log of a number greater than 1 is a positive number. There's a minus sign out here. So whenever the volume expands, the work is negative. Remember that fact later on when we talk about the first law of thermodynamics. This fact will be quite useful to you. Let's now look at the last of the 4 fundamental thermodynamic processes, the adiabatic process. As before, we have n moles of an ideal gas, and we assume that the initial state of the gas is described for us. So we assume that we know what the initial volume and initial pressure of the gas are, and we are manipulating this ideal gas in an adiabatic process. So the volume changes to some final value V sub F, suppose that number is given to you, and the pressure and the temperature might also change. However, there is no heat, so there's no thermal conduction. Because we're talking about an adiabatic process, Q must equal to 0. Calculating the work in this process is now a little more complicated, but once again, we start with minus the integral of P dV. For an adiabatic process, we need to now know that the pressure can be expressed as P initial times V initial raised to the gamma divided by V raised to the gamma power. Gamma is a constant known as the specific heat ratio. We'll learn a lot more about gamma in later lectures. We'll learn how to calculate it. But for now, what's important is that gamma is simply a constant. This expression for pressure is by no means obvious. Once we've learned a little more about adiabatic processes, we'll be able to derive this expression. But for now, you'll simply have to trust me that for an adiabatic process, the pressure can be expressed as follows. Using this expression in this integral, I can now write the integral as something that I can evaluate. P initial is a constant, so I'll bring it out of the integral. V initial to the gamma is a constant. I'll bring it out of the integral. And then the integral of dV over V raised to the gamma can be evaluated using the power rule. When we use the power rule, we get this expression here. Don't forget to plug in the limits of integration. When you do that, you get this expression here. Now, this expression can be simplified a little bit. What we have, for example, in the denominator is V final raised to the gamma minus 1. We can write that as V final raised to the gamma times V final raised to the minus 1 power. V final raised to the minus 1 power can then be brought into the numerator, and so we can express this mess here a little more simply as follows, as shown here. Then I use this same equation for pressure once again to recognize that P initial times V initial to the gamma divided by V final to the gamma must be P final. So I'll replace that entire thing with P final. I'll do a similar thing with the second expression, and I finally get the expression that I want. In an adiabatic process, work is equal to 1 over gamma minus 1 times the change in PV. Although it's not so obvious, once again, if the volume expands, the work performed in an adiabatic process is negative. So at this point, it may not be at all obvious why one would want to calculate the work performed in a thermodynamic process. We'll get to that in a later lecture. But for now, let me just summarize the 4 practice problems that we went through. We have 4 fundamental thermodynamic processes, and we systematically calculate the work performed in each one of those. We found that in isochoric processes, work is not performed, or the work performed is simply 0. These 3 expressions are important because they give us the work performed in the isobaric, isothermal, and adiabatic processes. In each of these cases, if the gas expands, the work ends up being a negative number, and if the gas contracts, the work ends up being a positive number. We're now ready to state the first law of thermodynamics. According to this law, the change in the internal energy of a system is equal to heat plus work. So when we heat a system, we're effectively changing the internal energy of the system. We're essentially changing the microscopic energies of the molecules or atoms of the system. But according to the first law, that's not the only way to change the internal energy. Work can also change the internal energy of a system. Note that the first law of thermodynamics is essentially a statement about conservation of energy. The first law is essentially saying that heat and work must change the energy of a system. That change might not manifest itself in the large-scale external energy of the system, but the internal energy of the system on a microscopic level will change as a result of heat and work. To use the first law of thermodynamics effectively, you often have to use a combination of these equations. In a previous lecture, we learned that when the temperature of a system changes, the thermal energy that must be transferred through heat or through thermal conduction is given by this formula here, where C is the specific heat capacity. On the other hand, if the temperature is not changing but the phase is changing, then the thermal energy that is transferred through heat is given by this formula, where L is the latent heat. In this lecture, we learned that work for various processes can be calculated using this equation here. To use the first law of thermodynamics, we often use a combination of these 3 to find Q and W, and then from the sum, we can find the change in the internal energy. Note that both Q and W can be positive or negative. When they are positive, we're increasing the internal energy. When they are negative, we're decreasing the internal energy. Let's end this lecture with a practice problem. Suppose 2 moles of air, which can be modeled as an ideal gas, initially confined to a volume of 50 liters at a pressure of 1 atmosphere, is heated in an isobaric process to a final volume of 70 liters. The molar specific heat capacity of air is 29.1 joules per mole per Kelvin. For part A, calculate the work performed in the process, and for part B, calculate the change in internal energy of the air. We're told that the process is an isobaric process, and we know that the work performed in an isobaric process is equal to minus the initial pressure times the change in volume. The initial pressure is given to us. It is given to us as 1 atmosphere, so you should be careful to convert that to SI units. In SI units, 1 atmosphere is equal to 101,325 pascals. The volumes are also given to us, but notice that the initial and final volumes are given to us in liters. We need to convert those as well. So we can say that V initial is 50 times 10 to the minus 3 cubic meters, because there are 1,000 liters to a cubic meter. And we can say that the final volume is 70 times 10 to the minus 3 cubic meters. Substituting those numbers into this equation, we find that the work that is performed in this isobaric process is approximately minus 2,000 joules. For part B, we need to calculate the change in internal energy. To calculate the change in internal energy, we need to calculate heat. In other words, we need to calculate the thermal energy that was transferred into or out of the system through thermal conduction. For that purpose, we need the temperature of the system. We are talking about an ideal gas, so we can use the ideal gas law to calculate the initial temperature of the system. The initial temperature of the system is equal to the initial pressure times initial volume divided by N times R. N is given to us as 2 moles. The initial pressure and volume are given to us as well. Convert those to SI units and plug them into this equation to find that this volume of gas is initially at a temperature of approximately 304 degrees Kelvin. We can also find the final temperature in the same manner. Again, we are rearranging the ideal gas law to solve for temperature. T final is equal to P final times V final divided by NR. Plugging those numbers in, we find that the final temperature of the gas is approximately 426 degrees Kelvin. Note that this is an isobaric process, so P initial and P final are equal to each other. They're both 1 atmosphere or 101,325 pascals. Now that we know the temperatures, we can calculate the change in the temperature and from that calculate Q. Q is equal to the number of moles times the molar specific heat capacity times the change in temperature. The change in temperature is found simply by T final minus T initial, which gives us a change in temperature of approximately 121 degrees. Plugging those numbers, we find that heat was added to the system. Approximately 7,000 joules of heat was added to the system. To calculate the change in internal energy, we simply add heat and work to find that the internal energy of the system increases by 5,066.25 joules. And that is the end of this lecture. Thank you for your attention.